All right, well, I always enjoy getting up on stage at SR Experts. And this topic in particular is one that's near and dear to my heart, IP and optical network interworking. It's something we've been talking about for years. In fact, I think the last time I presented at SR Experts in EMEA was on this topic. At that time, I was really using the opportunity, because it's more of an IP crowd at this event, obviously, to explain a bit of what was happening in the optical layer. And that was about 3 years ago. And the big topic then was this something we call CDC, connectionless, directionless, contentionless, and flexible, CDCF. So really, we're reconfiguring the optical transport network to enable a much more dynamic wavelength switching, so literally photonic switching in the optical network. That's now in place. And so this topic of integrating IP and optics has been a challenge, and one of the reasons it's been a challenge is because we didn't have that dynamic optical layer. Now that it's in place, we've been deploying it across the globe. We've been sort of revisiting, okay, how can we get these two to come together? So this is what I'll talk a bit about. We call this IP Optical Integrated Networking 2.0, and I'll explain why it's 2.0. But first, just I guess a bit of the motivation of why we really believe it's important to streamline the network and bring these layers together. And if you think of what's been driving the capacity, what's been driving the network builds over the last few years up until today, largely it's been rolling out broadband services, whether that's for businesses, business VPN, business internet, the wireless network, rolling out LTE, getting broadband in place in the wireless network, residential broadband. We've now built globally, all of you in this room, along with us and our equipment, have built a pretty impressive broadband infrastructure. It's not the end, though. We of course know that we need to continue to scale capacity, but we expect a whole additional wave of applications that will come onto this network now that we've built it. So evolving from just the basic broadband service to thinking about things like smart cities. How can you use that network to make cities more efficient, more livable? Manage traffic, manage parking, all sorts of great things we're doing with smart cities. Video, kind of turning video around from a consumer's watching video type of experience to video surveillance. There's many cities now that have cameras all over the place, and that's just going to increase. People are installing them in their homes and their doorbells. So much more video, bringing additional traffic onto the network rather than distributing it, actually capturing video in its surveillance. Then, of course, the goals of 5G and what we're trying to accomplish with 5G. And we're just at the very early days of 5G, completely re-architecting the wireless network, from the radio interface all the way through to the core, moving on to modern technology. And that's going to open up a whole additional wave of applications. Industrial type of IoT, where we can begin automating all sorts of processes. You can only imagine the types of things we can do there. We'll have mining machines that are completely automated, moving around, moving large volumes of minerals, and the list goes on and on. And so we're at the cusp of all of these new applications coming onto the network. We've got to make sure the network can handle it. And so what does it mean in terms of the traffic dynamics in the network? So if you think about what we've done to date, largely what we've been connecting is people. The internet, the broadband networks we built are largely there for information sharing that's ultimately delivered to a human being for the most part. And the way I think about this, human beings, the highest I/O port that we have is our eyeballs, right? That's the fastest way we can get information into our brains. And our eyeballs have kind of limited throughput. HD is sort of the limits of what the human eyeball can handle. Maybe a bit more, but we're kind of to the point where we can deliver as much information to human eyeballs, or to humans, at the rate that humans can consume it. So you'd say, well, that's it. We're done. The network's built. We don't have to do anything more. We just have to deal with the fact that humans spend more time on the network. But this new wave of applications will change all of that. So the first big thing, and this is already happening, is we're connecting machines. And it's not just the IoT type of applications you hear about, connecting automobiles, connecting as I said, mining machines, farming machinery, whatever it might be. But a huge, huge aspect is connecting servers. And we now have machines that are generating information, consuming information, without ever having a human involved, and doing that at insane volumes. Already today, the DCI networks are growing on an annual basis about twice the rate of broadband access and aggregation networks. The numbers that we hear are on the order of 100% traffic growth a year. So it's just exploding traffic. Then if we think about what that means in terms of the networks and how traffic flows, we've kind of had this very nice asymmetric type of architecture where, because it's largely information being distributed to humans, we could build things that sort of fan out in this nice asymmetric way. When you start dealing with machines, you think of video surveillance. Suddenly we're turning all those broadband connections into traffic sources. So our nice distribution and asymmetry is lost. We get this symmetric type data flows, which in the end, what does that mean? It's instead of kind of tree topologies, we're getting into more any-to-any type topologies we need to handle. So we've got to make sure the network can handle that and do it efficiently. And of course, given that we build the biggest, most powerful networks in the world, we've got to make sure that the networks maintain those characteristics. So we've got to be able to support scale. We need the ability to grow the network without thinking about it, right? It shouldn't be a challenge to grow the network because we know we must grow it, and we must grow it continuously. It has to be reliable. The networks that we build, you just can't have outages. When you're building a massive data center infrastructure like the big web scale guys build, they could have a huge portion of their data center go out. It doesn't affect any applications. They run somewhere else. It's not a problem. When you're building the access infrastructure, aggregation infrastructure, if you lose a portion of the network, that's lights out for some of your customers. And there's no way to recover because you can't move those customers or business sites to another location. So we've got to have very high reliability, very high degree of security. And if we want to make the network scale without thinking about it, the only way to do that is to automate. So we've got to have an automated infrastructure. And I know over the last couple of days you've probably heard many presentations about automation. It's a big focus for us here at Nokia. So we want all of those attributes. Now when we look at the IP network, and what we've been doing in the IP network over the years is putting a lot of those capabilities into the network itself. So we talk about security. We have things like policy-based routing, kind of control what traffic comes onto the network, how that traffic traverses the network. In terms of making it very robust, quality of service, of course, has always been a big part. Managing capacity with things like traffic engineering, augmenting the network with things like streaming telemetry so we have a better understanding of what's happening in the network, and of course automating it with programmable interfaces. So we've put these pieces in place. I would say today we have, as an IP network, we kind of hit those three key points from the previous slide, right? It scales very nicely, it's very robust and secure, and we're starting to get into a lot of automation, just in the early days of automation. So that's kind of come into place in the IP network. On the optical network, and many of you may be less familiar with this stuff, we've done the same thing. So, optical networks used to be fairly static in how they were built. You'd build a ring, you'd connect it to another ring. I'll talk a bit more about this. That has evolved with this technology listed here, the CDCF ROADMs, where literally we now have optical switching nodes that have some number of fibers coming in, and we can switch any wavelength across any of those fibers. So we've put that notion of wavelength routing into the optical transport network. We've also augmented the optical transport network with ever-increasing health analytics, pulling data out of the network. I'll talk an example of one of the things we're doing on a later slide, but just to give you an example, things like prefect error rates, which helps you to understand, hey, am I going to have a laser that fail? Lasers fail over time, so can you predict that and do something a bit in advance? So that's going into the network. And we've also augmented the optical transport systems with programmable interfaces. So we now have those interfaces on those systems. And so both at IP and optical layer, we have a lot of the tools in place. The big challenge that we faced, and we've been working this challenge literally for years, is how do we get these two to come together? We believe it's a must because there's no other way to be able to scale the IP network unless you understand what's happening in the transport. The transport is the lifeblood to IP, right? You can't move bits if you can't transport them. In the attempts that we've had in the past, we tried to get the protocols to talk to each other. We've got GMPLS running in the optical network to manage wavelengths. We've got MPLS and routing protocols running in the IP network to manage traffic flows in the IP tables. We tried to put them together with things like GMPLS Uni, so there would be some interface between the two. We could never really get it to stick. And the challenge here is that the reality is the optical layer is dramatically different from the IP layer. The constraints you use when you're routing something, you have to worry about gain equalization. You have to worry about how many amplifier hops that I go through. There's all these additional constraints. When you're building routers, we don't think about that stuff, right? We think about, what's the QoS, how large are the forwarding tables, what's my IGP topology. Completely different technical domains. So trying to get those control planes to speak to one another has just been a challenge because they're solving fundamentally different problems. So this is why we introduced 2.0. And what's different in 2.0? Well, the big difference is that we realized if we want to bring these layers together, trying to do it in the nodes, as I said, is very difficult because they don't speak the same language. But if we build software with our NSP platform, SDN software, we can embed in that software pretty detailed knowledge about both layers, and we can tie them together outside of the network. And so it's really this SDN technology that's enabling us now to realistically build integrated IP and optical networks where you have really cross-layer intelligence and can start making more efficient decisions about where and how to route traffic through the network. And I'll talk about what that means and how we use that. The other key point here is that it's super critical for this to be multi-vendor, right? First of all, there's optical vendors that don't make IP routers, and most IP router vendors don't make optical transport. Nokia is probably the only company that is a world leader in both. So if you're going to bring the two together, it's almost certain you will run into situations where it's multi-vendor. So we really needed this to be multi-vendor, and again, using the SDN layer makes that a bit easier, right? We can use software interfaces, a variety of different software interfaces to tie into different vendors. And so we've got the pieces of the puzzle in both of those layers. We now have the final piece of the puzzle to bring this together with the SDN layer that can now combine the two. So the question is, what can we do with it? How do we create value, and why do we care about bringing these two layers together? And there's really two key things that we focus in on. The first is just the efficiency in how we transport traffic across the network. Typically, as I said, the optical networks are sort of built in these rings. Sometimes they're in kind of U-shaped configurations. But you have a fiber run that terminates at 2 points. You close that loop and build a ring. And then where those rings intersect, where you have fibers coming into a facility, you want to connect them together. And traditionally, that's been sort of a manual connection. You take your ROADM A and ROADM B, and you plug them together. And that was fairly static. And that, of course, has now changed, where those ROADMs are now integrated into a wavelength switching platform, and we have the ability to switch wavelengths across any of those fiber routes. Now, in the old topology, what we ended up doing almost always is we would sort of go back to a hub-and-spoke style topology. Because the optical layer was so static, we'd bring all the traffic back to a central site where we'd have some routers, and we would use the routers to sort of route traffic across the different rings. That works for most traffic, particularly in this environment today where most things are sort of coming from the core and then fanning out. That hub and spoke works great. But as we move to these new applications where the sources of the traffic becomes less predictable, we're going to have much more meshiness, is the way I would describe it, in terms of the traffic. So that sort of hub and spoke topology doesn't work so great. So what we want to do is, by putting in this dynamic optical layer, we can now optimize the topology and make it much more efficient. So where you start to see traffic that's traversing more east-west rather than going north-south through a metro, you can start to route those wavelengths to directly connect the routers in that topology. And ultimately, this can yield pretty significant savings, depending on the traffic patterns that you have in the network. We've seen as much as 25% overall savings by really looking at the traffic demands and then optimizing the way the network is built and how you're routing the optical transport. So it can be pretty significant savings. So that's really the first area that we see. And then the second big area has to do with the protection schemes. And we've been talking about this for years. I think it's becoming more interesting over time as the traffic volume increases. So traditionally, you build a network. If you've got one service that requires sort of mission-critical operation, you're probably compelled to say, look, I need one-for-one protection. I've got to make sure that service is up. If something fails, it's got to recover instantaneously. So what we end up doing is we put in a transport layer link and then another transport layer link, make sure they're diverse on different fiber paths, pin those up, but we don't necessarily need all that capacity. We're just doing it for redundancy tied to some service that requires it. And of course, we can support that in this type of network, no problem. Then there's other services which maybe don't require the same level of redundancy. So you have high-value services. You don't want them to have outages, but maybe it doesn't have to recover instantaneously. You don't necessarily need the 50 millisecond. So with this dynamic optical layer, we have the option now to say, look, let's have at the optical layer a predefined backup path. It's not allocated yet, so I'm not using transponders. But if I do have a fiber cut, I can reroute, reconnect the routers at the optical layer. So very efficient, using the same transponders. I don't have to add additional transponder capacity, but I still get that dynamic failover. Now you need to be very careful when you do this. That backup path needs to be reserved. You need to know that the wavelength switching nodes along that path, that wavelength is available. So you're kind of pre-allocating the wavelength. But this is very efficient for, say, business services. It's not super mission critical, but you would like some backup. And the difference between these two is we've saved a bit of capacity here. We still have a backup path. We have to make sure the resources are there, but we're not consuming a transponder port on day one, right? It's going to reroute at the optical layer. And then you get your bulk traffic, bulk internet traffic, where, probably don't even need to recover necessarily at the optical layer. Often you end up with multiple links. So you have, 2, 3, 4 links between routers doing ECMP or something like that. And so this, we can just protect this at the IP layer. If I lose one of those optical links, it's not a big deal. I'm okay to accept I've lost some transponder capacity. I'll be a bit oversubscribed perhaps from normal, but you can make it work. However, we do have the option that if you said, well, if it's available, why not also try to reroute at the optical layer? So your kind of baseline is to say, it's okay, I'll just take that port out of operation. But if I have capacity somewhere else in the optical layer and I can reroute, well, let's reroute. And we call that sort of a floating backup endpoint. So the key point here is as the network grows and you begin putting more and more capacity on the network, if we just said, hey, our backup scheme is this kind of gold approach, you'd have one-for-one for all the traffic, which is not what we want. What we want to do is say, well, we need one-for-one, but just for a portion of the traffic. Let's use these other protection schemes that are more efficient. And then at the IP layer, we can use policy routing to make sure it's using the appropriate optical transport links for the different services. And so in the end, instead of 2x capacity for protection, maybe you have 1.2x capacity, so much more efficient. So those are really the two key areas that we're seeing by bringing these layers together, by understanding the services at the IP layer, understanding the protection schemes in the optical layer, mapping things correctly, we can get pretty significant savings and much more efficient operation. And of course, we do all of this through our NSP platform. Now there's a number of, I'll hit on just a few things from an operational aspects because the cost savings in building the network and CapEx are important, but of course, operations perhaps is even more important. So there's a number of things that we can do in terms of operational simplicity. So the first thing is just getting multi-layer visibility, right? Typically today we have the IP team, the optical team, they have completely different views. Bringing that all together in a common set of screens so you can get a chart like you see, where is it? There it is, right behind me, that sort of shows those layers and you can begin to understand how they are interrelated to each other. Second thing that we highlight is making sure that you have link diversity. Many of you have probably run into a situation where you provision a couple of router ports, you're like, great, I'm in good shape. Suddenly there's a fiber cut, and it turns out, yep, both ports were going over the same fiber. So there goes your protection scheme. By having visibility into both layers simultaneously, you can begin to make sure that, hey, I really do have diversity for my IP router interconnects. And then you can begin to think about, with this dynamic optical layer, what happens when I need to take a fiber route out of operation. You can start to plan for that. So obviously you have fiber cuts and you have to deal with it, but there could be other situations. Maybe you're upgrading one of the long-haul transport fibers, adding C+L, whatever the case might be. You can begin to coordinate and plan. So you can have a plan for how to reroute the traffic at the optical layer, reroute it, so haven't really interrupted any services, do the maintenance required, and then move things back onto that fiber route. So just another example. Now in terms of, so those are sort of like operational planning type advantages of having visibility into the two different layers. But of course, we want to deal with faults, and we want to deal with faults quickly and efficiently. So again, by having the two layers together, we can start to do some interesting things. So let's say we have a fiber, well, let's say at the IP layer, somebody notices, man, my IP service is out. What do you want? You want to know very quickly what caused the outage, so of course you can address it and get your customers back online. And so with these layers together, common software platform, we can correlate when there's an IP service outage, ultimately what's causing the outage. And so you get a root cause analysis, indicates, yeah, there's been a fiber cut or there's a bad transponder, something in the optical layer. You can now take action to go and address the root cause, perhaps take some action to reconfigure things in the meantime if you didn't have the right backup schemes in place. But you get that ability now to understand what's causing the IP service failure. And then there's a notion of proactive maintenance. I think I talked a bit about this on the previous chart. But again, the idea here is if I know I need to do, oh no, this is a little bit different, I apologize. Since I mentioned this earlier. So what's going on here is, as I said, we've added telemetry at both the IP and optical layer. This is an example of one of the things that we can do, which is monitoring what you see here. It's hard to see because the chart's so small, but this little green graph is monitoring the prefec bit error rate. So again, it's prefec, so it would be corrected with the FEC algorithm at the optical transport layer, but that prefec rate's going up. So at some point, the error rate will be high enough that FEC can't recover, and we're going to start losing packets and dropping bits. But since we can see that happening over time, we can, in a predictive way, say, hey, you're going to have a transponder failure sometime soon. You may want to take action to reroute traffic away from that transponder, put a new transponder in, or at least be ready in case it fails. So this is another example of, again, you can now see here's a failure that may occur in the optical layer. We understand what's that impact at the IP layer, and we can proactively and preemptively take action to correct the failure before it even occurs. Now, in theory, that could be automated. And so here we sort of indicate that you can monitor the health. NSP could have thresholds and do other analytics to determine, hey, this is a point where we really need to take action based on past experience. And again, over time, this gets more and more intelligent because as we're monitoring more networks, we get more data. We can run that through machine learning algorithms to get very predictive in terms of when a failure is going to occur. And we could potentially automate a closed loop action to reroute the traffic, raise a ticket to say, hey, we need to swap out a transponder. Then one last area that's really exciting. This one's particularly exciting for me because what I've mentioned so far is a bit of, if we bring these layers together, we get some nice potential CapEx savings as we scale the network. Of course, there's many operational aspects that get improved. What I haven't talked about is what does that mean in terms of enabling new services. So I think there is a potentially significant opportunity to enable new services if we get this type of infrastructure in place, and it's very important that it becomes fully automated and programmable. So the idea here is, imagine if you have a dynamic IP and optical network. You've got customers that are going through the challenge of, my favorite example is cloud migration. So they're They're moving their enterprise applications from their own private cloud on their premise. Maybe they want to use AWS, maybe they want to use Google Cloud, maybe they want to use OVH or some other smaller cloud provider. And they're going through that challenge. And so there's all this data that needs to move around. They want to move it into one cloud or the other. And of course, all those cloud providers, they're not in a single location. They've got data centers all over the place, often, sometimes many, even within a metro region. That will increase over time as we move to edge cloud. So you got all this data that you want to move around. I think there's a great opportunity to create a service for customers. And this happens already today in exchanges, where you kind of get capacity in the exchange. Then you have programmable interfaces that allow you to determine, well, who do I want to connect with. Here we can do it at the optical layer. So imagine you have router ports that you're provisioning at a customer site. Say they need 10 gigs of capacity. You say, well, let's just provision 100 gigs. And so as they want to interconnect to different cloud providers, you've got a programmatic interface that ultimately is seamlessly tied into the cloud provider's software stacks. So when they say, I want to do a migration, move this workload from my data center over here, it automatically dials up bandwidth, does that migration, and when it's finished, it releases the bandwidth. Perhaps reroutes the bandwidth somewhere else, whatever the case may be. And then over time, as you add more and more capacity, you say, well, I don't want one router port, I want two. And maybe I want to reroute at the optical layer which data center I'm connecting to. These are all becoming possible, right? Bandwidth on demand has been one of those things that we've talked about a lot. The use cases were always a bit of a challenge. And so I think that with this evolution to cloud, with the tying together of the IP and optical layer, we're in a position now where it's becoming realistic to be able to offer a very interesting high bandwidth on-demand service that I think enterprises will love to consume. And these are the kind of services we need. We need services that our customers are consuming without us even knowing about it, right? We provision the raw capacity, hand it over to them, let them consume the services. So this is one example. And I definitely think we'll see this rolling out over time. It's already happening today with direct connect type services, not in this sort of programmatic on-demand fashion, but I think that's the next step we can take. But once again, it depends on having the multi-layer SDN coordinated IP and optical transport infrastructure in place. So again, I'll just summarize. There's really three key points here why we believe these need to come together. Again, it's not for technology's sake. It's driven by cost synergies. It's driven by operational simplicity. And it's driven by new services and creating service velocity. So thank you very much.